All right. So last time we just talked about the piecewise dependent functions, based on sets. We defined uh, piecewise dependent functions um, based on the sets of ordered pairs. Okay. Which was the main two we used for functions in this course. We did a few examples of piecewise dependent function. Basically, the idea is you can partition the domain of a function into several parts and define different rules for each part of the domain to the codomain. And that will give you different formulas for each part of the domain. Okay, there is an important idea or term concerning to the piecewise defined functions, and that's the characteristic function of a set. Okay, so because we partition the domain into different parts, then we can distinguish those parts by the so-called characteristic function. Okay, so let's just start from a set A, usually the domain of a function, and let's say S is a subset of this set A. Then the characteristic function of S, the subset S, is a function defined by this rule. Okay. The function value is 1 if X or A is in S, and the function value is 0 if A is not in S. So this function is denoted by chi sub S. Okay, to denote the characteristic function of the subset S. So this chi of A is equal to 1 if A is in S, and is 0 if A is not in S. So that distinguish the set S and the complement of it. So this function chi sub S is from A to the set of 0 and 1. All right, it only has two function values, 0 and 1. And it takes value of 0 if we're not talking about points in S, but it is 1 if we are talking about the points on S. All right. So remember the domain of this function is set A. A is not S. Okay, it's this the whole set of A. So this function can be easily understood from the picture below. If the definition makes a little abstract. Okay, so let's say we have a set A, and S is a subset of A. So that's part of it. So we use a different color, the green color for set A is inside A. All right. But then it maps, this whole set A into two values. It maps this set subset S into 1. Okay, and maps the remaining part of A not in S to 0. All right. So so the function chi sub s indicates whether an element belongs to S or not. So that's the whole point. You know, but the 1 or 0 output, you can think it as a yes or no. All right. If the function value of chi is 1, then we know we are talking about the points in S. If the function value is 0, this chi is 0, then we know we're not in S. All right. So this is especially important or useful in piecewise defined functions. When we try to write down, for example, one formula for piecewise defined functions, we can use the function chi, the characteristic function chi. We can use the characteristic function for each part of the partition of the domain. All right, so we are going to discuss any well, we do discuss some examples in here, not too much. Okay. So it can be useful to think of the characteristic function as a method detect it beeps, which gives the output 1 when you are near elements of S. The method when it's silent, given it gives output 0 outside of S. Okay. So as I said, the notation cancel base does not indicate domain of the characteristic function. Okay. It has nothing to do with domain. All right. The domain is typically either understood from context or explicitly stated, for instance, by saying K sub S from A to the set of 0, 1. Okay, so the domain is A, not S. S is just a subset of A. Keep in mind. Okay, let's just graph this characteristic function. So in this example, the set A is the set of real and whole real numbers, and this set S is the numbers from 0 to 1. That's the interval from 0 to 1, including both 0 and 1. So that's a subset of A. So there's a closed interval. So then, so what is the graph of chi? In this case, chi sub S, which is from A to set to the set of 0 to 1, which is R to the set of 0 to 1. So if you still remember the definition of the characteristic function, it takes value 1 when x is in S. So when x is between 0 and 1, including 0 and 1, the function value is 1. So y equals 1 for x from 0 to 1, including the endpoints. Otherwise, it takes the value of 0. So in the other part of the x-axis, the function takes the value 0. So it's just the other part of the x-axis with the endpoints not included. Okay, so we have an open circle at the origin and at the point of x equal to 1. So that's the graph of this characteristic function. Any questions? If no question, then we go to the next topic. It's called well-defined functions. Okay. Well, this is the important concept, a well-defined function. Remember when we talk about function, we define function. It says for each value of the x in the domain, it only maps to one value in the codomain. In other words, a function cannot have two values for a fixed x. You cannot have two yy's for each x. So if you do have a case when you map one x to two y's or several y's, then the function is not defined, or we say it's not well-defined function. Okay. So sometimes when defining function by rule, the rule depends upon a choice we make. Well, what does it mean by here? This happens especially when we talk about functions based on classes, congruence classes. Remember? For example, if you define a function f from z5 to z5 by this rule, f of a bar equals a square bar, it means, remember, a bar is the notation for the class, congruence class. So a bar means a class as numbers with the same remainder as a when you divide the number by 5. Okay, and we map it into a square bar. So we map it into another class defined by a square. Okay, so you just take the square of any number in that class and square it, and then find out which class it belongs to. We know there are 5 classes in Z5. Z5 is a set of 5 elements, corresponding to 5 remainders. When you divide the integer by 5, you only get 5 different remainders. So obviously, this a square bar is one of those classes or remainders. So we want to make sure this function makes sense. So what does it mean? For example, if we choose different values for the same class, choose different integers from the same class, then obviously when you take the square of the number, you'll get different numbers for the 2 squares. And when you try to classify it, which class each of the square is, we should end up with the same class for the function to be well defined. You cannot have different function values or different classes corresponding to the same class in the domain. All right. So so this is the rule. So this rule depends upon choice we make, right? You choose different values of a in the same class, and the rule involves the square and class, but we can have different choices of the class A from class A. So we need to verify this function is well defined, basically. So where are we making a choice? We choose representative A in Z for the congruence class A bar. Okay, you choose, for example, the two different integers in this same class and see if we end up with the same class in the function value. Okay, so so that's the rule really is choose a representative for this class, square the representative, and then take class corresponding to this square, right? That's the rule. For f to be a function, we must make sure that the output does not depend on the choice representative that we make. That's what I said. For instance, the congruence class 3 bar. Okay, so that's the class of integers divided by 5 to get remainder 3. So you have a bunch of numbers when they're divided by 5. They all have the remainder 3. Okay. So this congruence class is the same as congruence class of 8, of course. 3 and 8 divided by 5, we get same remainder 3. Okay, so but so they are in the same class. All right. Modular 5. Okay. So do we get the same output using the representative of 3 as we do with 8? If we do that, so for example, if we choose 3 as the representative, then square of 3 you get 9, and then you divide by 5. The remainder is 4. So we got the class of 4 bar. If you choose 8 as the representative from the class of A, and squared, you get 64. 8 times 8. And 64 divided by 5, the remainder is 4. 60 is a multiple of 5. So we got 4 bar again. So they're the same class. So that means we got the same output using different representatives from this class in the domain. So this function is well defined, but it is also easy to prove it. So we'll show that this works in general, for instance. So, for example, if you choose two numbers, A and B, they are both integers, and of course you want them to be in the same class. So A bar equals a B bar. So by that, it means that A and B have the same remainder modular 5. When they divide 5, they got some remainder. So using the properties of modulus, I mean the congruence relation, you can multiply A by A and B by B. You can multiply two congruence relations, left by left and right by right. So if you do that, A times A, and B times B on the left and on the right respectively, you get A squared congruent to B squared modular 5. And that's easy to prove, actually. By the way, this property, we already discussed this property in the other class. So that means obviously, that means A squared bar equals B squared bar. Okay. They're in the same class, modular 5, right? That's what it means by this congruence relation. So then we see that f of A bar equals A squared bar, but that's the same as B squared bar. So that's also f of B bar. So this function is well defined. Okay. So you can actually write down the function explicitly as the set of ordered pairs. We only have 5 ordered pairs. Remember, there are only 5 classes in Z5. So these are 0 bar, 1 bar, 2 bar, 3 bar, and 4 bar. And paired with each of the class of the domain, we can easily find the function value for each class. So obviously, the 0 bar will be mapped to 0 bar. So 0 squared is just 0. So we just get 0 bar in the second entry in the order pair. And for 1 bar in the domain is square 1, you get a 1. So the function value is also 1 bar. Okay, so we get another order pair 1 bar, 1 bar. And for 2 bar in the domain is square 2 equal to 4. So the function value is 4 bar. So that's the third order pair, 2 bar, 4 bar. And we just did a 3 bar. We get the 4 bar. Okay. So that's another order pair. And lastly, for 4 bar in the domain, if you square 4, you get 16. 16, if you divide 16 by 5, the remainder is 1. Okay. That's easy to do. So the function value is 1 bar. So the last order pair of this function is 4 bar, 1 bar. Okay. So that's the whole function. Okay. We just talk about 8 bar. If you square 8, you get 64. So the order pair is 8 bar, 64 bar, but that is the same as 3 bar and 4 bar. If you divide by 5 of 8, you get 3 as the remainder, and then you divide by 64 by 5, you get 4 as the remainder. So that's the same as 3 bar, 4 bar. So the order pair of 8 bar, 64 bar is the same as the order pair of 3 bar, 4 bar. All right. So it's just in the fourth order pair in this function f. All right. So let's just look at one more example. Define a function by the numerator function. Okay, so this function is from Q to Z, from a rational number to integers by the rule of this. So if you are given a rational number, which can be written as n over d, okay, and we just take the numerator as the output of this function. So for example, if we plug in 1/2 for the x, and then we should get 1 as the y value, because you just take out the numerator. But this is not well defined. This function is not well defined. It's not a function, actually, because you can also write 1/2 as 2/4 or 3/6 or whatever. And when you use the rule to take the value of the numerator for 2/4, you get 2. So for the same number in the domain, you get 2 or more different values in the y. In this case, we're talking about 1/2, but we already got 2 different outputs. 1 and 2. You can also get 3, for example, if we write the 1/2 as 3 of 6. So that function is not well defined. Okay. But you can modify the rule to make the function. If you change the rule as to take the numerator of a fraction of d when the fraction is in lowest terms with d greater than 0. Okay. So if you define the rule as the numerator of the reduced lowest term with the numerator greater than 0, then that will define a function because there are not two different ways of writing a fraction in those terms. In other words, you can only write reduce a rational number into lowest term uniquely. Okay, there's only a unique lowest term of any fraction. Of course, we're talking about the denominator greater than zero. And that's necessary. If you don't specify that, then you can actually, keep the same fraction by changing the signs of both the numerator and denominator. And then you're going to get the opposite numbers in the numerator if you do that. So we have to require that the denominator to be positive. But the numerator then can be both positive or negative or 0 sometimes. Okay. So that's another example of a well-defined or not well-defined function. All right. Well, let's look at one more example of function or relations between congruence classes. So if you try to define a function f by the rule from z3 to z by if a bar equals a, does that give you a function? No, it's not. Because in a class, congruence class, you have infinite many numbers with the same remainder. But if the rule is the value of the function is then the integer you represent, you choose, then you will get the infinite many numbers for the numbers inside one class in the domain. So these three, we can actually write the functions explicitly by the order pairs. I mean, not the function, but its relation. So for example, if a is 0, then you square, not square, then the output is 0. Okay. You just take the value of a. So that's the first order, 0 bar 0. Okay. Keep in mind the function value is a number, is not a class. Okay. And if you take a equal to 1, then and the output is 1. So the second pair is 1 bar 1. And if you take a equal to 2, the output is 2. So the third order pair is 2 bar 2. And if you take a equal to 3, you get output 3. So the third order pair is 3 bar 3, and similarly the fourth order pair is 4 bar 4. But you can see 3 bar is the same as 0 bar because when you divide by 0 and 3 by 3, you get same denominator, which is 0. Okay. So then for the same input in the domain, you get different results in F or in the codomain, namely 0 and 3 in this case. Okay, 0 bar is the same as 3 bars. Say they are in these three. So f possesses two distinct order pairs, 0 bar 0 and 0 bar 3, that both have 0 bar as first coordinate. So if it is not a well-defined function, it's not a function actually. And you can actually find a number of second number in this pair, 0 bar 6, 0 bar 9, and so on. Okay. One thing, okay, we need to be careful about the wording, about the word-defined functions. Let's just make this definition clear. Okay, so suppose that we try to define a function f from a to b by a rule from set A to set B. If the rule produces multiple images for a single element of A, then we say that f is not a well-defined function. It is not a function. Okay. If the rule for f produces a single image for each element of A, then we say that f is a well-defined function or a function in short. So this is the one thing we need to be careful when we give a rule. It's usually not necessary to check that it produces a well-defined function. Most mathematical operations produce a fixed result for a given input, but sometimes it does not. So we need to be cautious. And the key indicator that which determines whether you should check that a function is well-defined is that the elements of the domain can be written in different ways when plugging into the rule, such as when working with equivalence classes and rational, rational numbers, as we just saw the example before, a couple of examples before. I guess we didn't finish the section. We still have quite a little bit, and we cannot finish it today. So let's just stop here, and we'll finish this section next time. We're back. We're back from spring break. Any questions?
No, nothing at all.
All right. So I'll see you in 10